Welcome back to the stream, folks. Audio quality might be a bit hit and miss this time since you might hear the power washers outside, but there's so much good reversing I couldn't resist streaming, so we're gonna have some of that anyway. As always, I think my cat wants some attention to open up the stream. Oh, I think he brought me a bolt. It will be nice having a robot to follow this cat. Which is, of course, the ultimate goal here. This gimbal goes on a little hovering robot that'll be pulled around on wires by some winches on the ground. And ultimately, this will all be for following around my cat with live control over Twitch. But right now, we're working on sub-problems within sub-problems. So there's a gimbal that's designed for quadcopters that I've been modifying for this occasion. And along the way, oh look, there's a ding. I guess that was a question from Ken asking what I'm going to do about focus for the robot. So my plan was to have the lens set to a fixed focal distance, which would kind of define some of the parameters for how you would use the robot. Because I figure some of the interest in it is going to be, I think I want the robot to always be about the same distance from the cat anyway, so I didn't really see that adding a motor for focus would be a huge improvement. I'd rather just set that to be kind of one of the parameters of the game, is that you have this camera with kind of a fixed distance and you can kind of like search around for the cat. So for focus assistance, instead of changing the focus, I actually just want distance feedback so I know how far away the object you're pointed at is, and then I can help move the robot to the right location so that you're the right distance to be focused, and that's how I was going to approach that. So for the sensor, I have a LiDAR sensor, which is a LiDAR light, is the brand name, from Pulsed Light. It's basically just a time-of-flight distance sensor which uses a really, really brief pulse of intense infrared laser light. And yeah, that thing was a little loud. Maybe I can turn that a little down. I think it'll be quieter next time, but I'm not really quite sure by how much. Hey, too. So, we had this gimbal that I started to modify by making new brackets and running tiny coax through the joints, and then got a little bit ambitious with trying to figure out how to control it over something lower level than the kind of RC pulse width modulation style inputs. Discovered the serial protocol, and then around that same time ended up sending it a malformed packet that, well, doing kind of a range of things that ended up basically destroying the calibration that was saved on the gimbal and causing it to be completely unstable when it powers on. So after that point, we did a bunch of reverse engineering, starting mostly with just looking at the protocol as the Windows software that it comes with would do a little bit of setting manipulation just to do things like change the rate that it's following the heading at. And just by extrapolating from the parameters that we did see, I figured out, well, it was really a team effort. It was, a lot of people in chat contributing. So we ended up figuring out that, kind of figuring out this sequence of protocol commands that would let you read and write to a 16-bit parameter space. And then we started trying to figure out, well, what are all these parameters? And so it turns out that they're persistent, stored in flash, that it's pretty easy to mess them up. Most of them seem to be baked into the firmware. So when you flash a new firmware, it seems overwrite most of those parameters. But I think, it will, actually that's probably not true. When you reflash the firmware, it's probably actually taking care not to overwrite the parameters, but the firmware image contains a set of defaults. So even if that's not being programmed every time we update the firmware, we can at least look in the firmware image and find the defaults. We can also get defaults from a spare gimbal, which has a working calibration. So a couple of things really opened up really recently. So yesterday we got the firmware decrypted and started poking around inside the firmware. Let's do code here. And so that actually revealed, well, a few interesting things. The parameter space, it turns out, is just sitting in RAM. It's same format in RAM and in Flash, so we can verify that. The commands that read and write it don't have any bounds checking, so that's one way that we could have crashed it before, is by sending a write command that was not bounds checked at all. Oh no, another stream. Yeah, sorry. Hey Tuco, are you around? Oh, there he is. Cool. So yeah, lots of discoveries. I think the most interesting discovery, well, I don't know, there's a lot that we found inside the firmware that could be interesting. One thing that I want to look at specifically is a command that I think is related to how they do the calibration in factory. So there's my theory about what's going on at this point is that they would have set most of the commands to fixed values that are the same for each gimbal of a particular model, and those parameters are stored in the firmware image and just burned on during factory programming. And then after installing the firmware, they would have done a separate step, probably as part of their factory test harness, that moves the gimbal to different positions. And I think it needs 2 reference positions, because there's this command that we just saw in the firmware that we haven't seen any of the tools, at least some of the tools we have, send, which, if you look at the implementation, it's actually just copying the current angles into one of 2 different slots. I think the cat's not being cooperative, so let's just go right into the code here. Welcome back to the computer here. Let's get IDA open back up. So this is going to build on a lot of stuff from yesterday's stream. In the first half of yesterday's stream, we were just experimenting with the parameters using a UI tool that I wrote with a little bit of JavaScript to just let us graph parameters and poke at them in real time. And that was enough to start getting some more of an idea of what the parameters are, and we have a few of them pretty well figured out at this point. But I was still just kind of blindly trying to set the parameters to get a better calibration, and I was expecting to find maybe one that was a center position for all 3 axes in the magnetic angle sensor's coordinate system, and then maybe another one that was like gains that were calibrated in the factory. I think the gains are all just set ahead of time. I don't think the gains are calibrated. I think the calibration just consists of 2 reference points. So I think what they do in the factory is, I think one of them is the center and one of them is something else that's relevant to how the motors are lined up. And then based on those 2 reference points, it calculates all the other factors it would need. So I think that's why we were finding that, if I was adjusting one of the reference points, it would seem like in a particular range it was affecting the gain, and then it would like hit some point where it would cross over and then the gain would be negative. And so I think what we were actually seeing was there was some other gain-like factor that was being derived by subtracting those 2 reference points, or something along those lines. So I think what we're going to end up needing to do is to make our own calibration tool that starts out with the defaults from the decrypted firmware image and then goes through and sends this command that we found to capture 2 different angles from those 2 different reference positions. So that's what I want to work to in this stream. I also think I want 2 different subtools. So first I'll just want a little tool to extract the defaults from the decrypted firmware, which is pretty trivial, but I just need to write a few lines of Python to get that in a usable format. And then we could just jump into writing a tool that applies the calibration, but I first need to know what the 2 calibration points are, like how to actually aim the gimbal in these 2 different positions. I'm pretty sure one of them is just centered, but the other one is less obvious, and I think the quickest way to figure out a correct positioning for that is to look at the gimbal that's working. And I think I just want to write a tool that's effectively just checking calibration. So it'll read the current angle and report the difference between the current angle and the 2 calibration points, and then I'll just move the gimbal until I can get each of those to 0 and see where it's pointing. So this is the firmware image, and this is the cat. Hey cat, what do you want? As always, the cat just wants to play Bolt. Cats just want to play Bolt. That's how they work. Maybe we can move this. Good job, Tuco. All right, so firmware, pretty interesting so far. Most of the investigation, well, I think the most useful investigation so far is centered around finding things that are related to the serial port. So if you go, that table was maybe a little bit heavy to pick up the way I picked it up. Oh, Michael asks, will Tuco Flyer have a chat-controlled bolt launcher? I really think so, yeah. My goal is to get the camera control up and running and then to work on the bolt launcher. I don't know if the bolt launcher will be on the Flyer itself. I think it might make more sense to have perhaps multiple bolt launchers kind of stationed around the shop that you can kind of send commands to. And that's still going to be an interesting design. Like, I think it'll need to make some kind of noise to signify that it's going to launch a bolt, and then it, kind of like some bolt rumbling or something, and then like, pew, and then it launches a bolt. And I think we might need to have a way of doing that in multiple parts of the shop. So that sounds fun. There might also be something I can just mount on. There's like a railing up there that I could attach a bolt launcher to that could fire down, but I think Tuco would be more happy with something that's like at ground level, that's kind of like near him, that he can like stalk, and then it'll like make some noise and then shoot the bolt and he can like rush after it. I think he'd really enjoy that. So glossing over some of the steps from before, we already found the load address of this firmware file is at hex 4000 or 16 kilobytes past the beginning of flash memory. So that means this actually has a pretty large bootloader. The bootloader is an entire 16K, or at least that's how much they've reserved for it. Oh, that was a much more reasonable volume. Yeah, I'll enjoy having the bolts. I'm not quite sure how this project is going to go. Like, I could see it going so many different ways. Like, maybe I'll just build this and nobody will care and I'll move on with my life. Or maybe I'll build it and it'll be super popular and people will be trying to troll me with it all the time, like trying to race it back and forth or shoot bolts into my head, or I don't know. So I think this structure here at the load address is the interrupt vector table that we end up getting, that we end up switching to after the bootloader switches to the application. So all of this unknown space up here is just the bootloader that we haven't read in yet. Then this is the actual app, and this is the interrupt vector table. And on ARM, those start with a stack pointer, and then an entry point, then some fault vectors, and then these are hardware interrupts. So the easiest thing to do really is to just find the hardware interrupts that relate to serial ports and then just trace them. And so we found that it looks like it's using serial port 1 and 3. And I just started looking mostly at serial port 1. And so if we follow the interrupt handler, there's a couple of levels of indirection, and then a yelping cat down here. What are you doing, Tuco? Oh, there's the bolt. He just always wants that. So a couple of levels of indirection in the ISR. All of these addresses that are in like the 4 region here, these are hardware, and you can look them up in the STM32 datasheet, and this is just more UART related stuff. And so the UARTs all seem to be based on this kind of shared FIFO data structure. The 2 serial ports use the same kind of data structure, it looks like, but there are different instances of the functions. So in the interrupt, we're actually just, if you trace this through, this is the data register, and if you look at R5, it's storing this in something relative to this pointer, which comes from this data structure. And so if you follow this, you can find other instances of this data structure. So who else might be using this same FIFO? And so this is in RAM, but you can find cross-references to it. And so you can find, so we had already found out that this was like an initialization function, so that's probably not going to be super interesting, but we might find interesting references there. Then this is the ISR that we were just looking at. But then down here, this is a reference to a function that I was calling serial1 poll. And Windows update. Oh geez, that's not what I want. Please later. This is just a VM anyway. So if we look at this one, if you look at the, hey Tuco, you're not really helping. So this has a loop, and looking at the structure of this, it's actually just called at some points in the main loop, but it doesn't seem like, I thought that first of all, this might be something that like reads from the FIFO, so you would expect it to return a character, but it's just being called without really any regard for inputs or outputs, it seems. If you look more closely at it, it's looping here, and every time so if you look for byte-wide loads, here's a byte-wide load. So you can see that it's loading 1 byte relative to an array at OC plus this pointer that it's getting from the FIFO. So this is going to be like the beginning of its actual FIFO buffer, and it's pulling out like head and tail pointers and then like adding. And so this is the FIFO read, and the result ends up in R5 because that's where the byte-wide load goes. And this all happens in a critical section with interrupts disabled. But then after that, it's actually just like dispatching that byte to some handler. So we followed that into this function, serial1 handle read. And if you see the graph down here, this was tripping me up a bit because it has 2 separate switch statements, and it was a little hard to keep the 2 separate in the flow graph on such a low-res monitor. But this switch statement is a state machine that receives the different parts of a packet. So basically, that packet receiver that I wrote in Python a while ago based on just looking at the data on the wire, this is doing the same thing. This is just taking the framing of the packets, looking for that 5A, A5, yeah, A5, 5A is the beginning of the packet. So state 0 is looking for A5, state 1 is looking for 5A, then it looks for then it stores like the target microcontroller and the command, and et cetera, and it keeps track of a CRC, and it stores it into memory as it goes. And after it receives the whole command, then we end up in this state machine, or this switch statement over here. Yeah, so this is the last state of receiving a packet in that state machine. It checks the CRC, and it also checks to see if this microcontroller is the current microcontroller. If not, it sends it elsewhere. I'm assuming it buffers it and retransmits it later, but I haven't looked closely at this code. If it's for the current microcontroller, which in this case we're disassembling the firmware from MCU0, I assume this is just like a compile time variable that they set. So this code would end up getting generated differently in each micro. So if it matches the current micro, which in this case is 0, then it goes to this other state machine, which is just packets or command types. So this is finally where we can start correlating this exactly back to the commands we know about. So for example, there's some interesting ones like this is the command that we send to prevent normal startup when the PC is attaching, and we can see this flag that gets set. So that flag might lead to information about the distinction between like PWM input and serial input. We could follow that thread. This is the set command. So this is how we set parameters. And it's a 4-byte command. It has a parameter number, then a byte that I'd always seen as 0, and then a 2-byte parameter value. But if we look at this, we can see that this is reading 2 16-bit values. So R2 is the parameter value. This is coming from the payload buffer here is at address OX100 after the buffer at R4. Tuco, jeez. So this is just looking at the parameter, which is passed in over the serial port. And the first half of that is being interpreted as an unsigned 16-bit value, which we're just adding to, we're using this as an array index down here. So this is effectively just writing 16 bits to an address that we have, 128 kilobytes of reach, basically. So this could write to, I think, all of RAM, because this buffer is pretty much at the beginning of RAM. So there's maybe parts of, maybe some stuff at the very beginning we can't access, but so this is probably how I crashed it before, because I was playing with this command and I probably just overwrote something that ended up causing some cascading problem later on. Maybe I caused it to splat some stuff elsewhere in memory and then write it to flash, or maybe I wrote it to flash myself. There are a lot of ways that could have failed. And then correspondingly, this is the peak, the way of getting a command. So it actually is using just an 8-bit address, which is interesting. So you can't read all of RAM with this, but you can write. And you can also kind of get a sense for how replies are formulated. This is, I think, the code that ends up sending the response. So anyway, that all is pretty interesting. Also, this is the command that saves parameters to flash, so that's something we can follow. But I think what I want to explore right here, this is a command we haven't seen before. So this is command OC, which I've been calling unknown. I'm going to call it calibrate. I wonder if that was intended to be a mnemonic, like C for calibrate. I don't even know if they're used to seeing these in hex or in decimal. But this looks like it takes a 1-byte parameter. And we're handling 2 different cases. So there's a 0 case and a 1 case. So this is a compare and branch if not 0. So if it's not 0, it goes over here, which means this is the 0 case. If the parameter is 0, these are 2 items that we already figured out in that 16-bit parameter space that we can read or write. This one is the angle from the magnetic angle sensor on the current axis, and it's just copying that to the parameter that we already knew was the center. So if we give it this calibrate command with a parameter of 0, that's locking in the center position. So that makes a lot of fun, or makes a lot of sense. That feels really fun to have that connection. And then we get a response from this command, so if we care, which we probably will. So then up here, this is the 1 case. So we're comparing that thing that we checked from the first byte. Is it actually 1? If it's not 1, then we actually just go send a response anyway. So the response gets sent regardless of whether the parameter was valid, which is maybe a little weird. But if the parameter was 1, now we're storing this. So it's the same structure. We're copying the magnetic angle to some other thing. In this case, this is another old friend. This is the parameter that I had been assuming was something related to the motor alignment. And I wasn't sure what the units were, but this makes it pretty obvious that it's also another angle. So, I'm just catching up on chat again. Yeah, one of the ideas for tracking Tuco was definitely going to be using the thermal camera. I think maybe the best way to do that is to have the thermal camera be stationary and somewhere above the robot and the cat, and then to just search for the 2 different thermal signatures of cat and robot and look at the delta between them and send commands to, close the distance there. Which, doesn't really work in 3 dimensions, but maybe you can adjust for the gimbal angle. But yeah, so this makes it pretty clear that 6.4 and 4D are both calibrated angles of different kinds. I just don't know exactly what that angle points to. So I think that's the next thing to do, is to make a little tool for checking the calibration on an existing gimbal, like an existing calibrated gimbal, and then run that on our working gimbal and see what that actually points to. So let's go back in Raspberry land. All right, so here we are in the FY Gimbal repo on the Raspberry Pi. And let's just make sure first that I have this, that I have the notes on these 2 parameters. So 2C is definitely the current angle. That's right. 4D is definitely the center angle. Cool. And I even noted that that's stored with command C, parameter 0, and then 6.4 stored angle for command C 01. Okay, cool. So I'm just going to copy this to give us a starting point. Param dump. Let's call this calibration checker. I've rebooted this machine since the last time I had this mounted. Okay, so there are a few parameters that we care about. And then there's, I'm going to call these calibration slots. Actually, let's just map these. Okay, and we want to do this in a loop. And I think we just want to print out the current angle, the calibration slots, and the differences between them. This would be a nice time to have like a vector data type for this. I think this can be a one-liner actually. There's got to be a better way to do that. Is that even valid? Okay, I guess that works. So, I should really learn how to use the new formatting in Python, because I think it's actually a lot easier. I just keep forgetting how it works, and I use the old style % stuff. What is this? Oh, that's kind of handy. Somebody made like a whole separate document just for this. Yeah, that makes sense. That reminds me of C#, which I also don't know that much about, but it feels familiar. So I'm just going to feed locals into this, why not? Actually, I think I do need to do some calibration, or some calculation here. So current. Something like that. Oh, yeah, I wanted that to be 0. So I think this is just going to give us the data we want in a loop. So it's going to poll these 3 locations and print out the current values and the differences. So we can try this on the on the sacrificial / modified gimbal first. Okay, so it's waiting for the gimbal. Connected. Oh yeah, let's turn off the verbosity here, because that's going to be hard to deal with. I think that's working. So these values are going to be pretty meaningless right now for this gimbal, but we can at least see that they're updating right and this isn't crashing. Let's get the overlay on so we can see the gimbal too. Okay, this is our calibration checker. So let's just swap out the working calibration for this gimbal, physically swap out the other gimbal and run the same program. So unplug power, unplug this big plug. Carefully deal with the coax, which is not on the same plug because coax. This is where the video is going through. BNC on one end and 0.81 millimeter diameter coax, which is what actually goes through the gimbal to reach the camera. When I say through the gimbal, I literally mean through the center of each of the motors, which is how the wiring works in this. Alright, there's my modded gimbal with its camera. Here's the normal gimbal with its normal camera. Okay. Make sure I have enough slack to plug in this cable. Okay, power's off. All right. So if I run this script and then plug in the gimbal, then it'll prevent the gimbal from powering on normally, and it'll let us dump out the calibration. So calibration checker. There we go. So I'm going to try to hit the stored calibration point 0 first, which I expect to be the center. That seems very centery. So the diff from cal 0 is near 0 when I point the camera straight forward. This is very sensitive. Okay, let's try hitting the other stored parameter now. Huh, that's not quite 90 degrees. And it's not the end stop. I wonder what that is. So that's the yaw axis. It's holding that one axis in place. I'm going to have to take out the camera because that doesn't quite reach. So they must do this with the motors turned off. Oops. Man, these gimbals are very wobbly to store. Anyway. That's interesting. These seem like very arbitrary positions. So I'm wondering if this has something to do with the way the motors are aligned. Yeah. It's like right there. That's a weird position. So the camera would normally be pointing out leftwards there. This has got to be related to the motor phase. I wonder what my phone has been trying to tell me. Oh, I've got to do something really quickly for my neighbor. I'll be right back. Do we have cat cam active? Tico, this is yours. Ow. Ow, ow, ow. Not a stub toe, I stepped on a bolt. That's Lego in heel, basically. Ow. Paul is asking, are the weird positions just where the magnetic poles end up when the magnets are glued in? So, I mean, the magnets could be totally... So all of this is relative to the magnets. So my question at this point is, what is the other reference point here? And so we're already calibrating for the magnets because, like, assume the orientation of the magnets are all just completely arbitrary. But what is the other reference point here? Aw, Tuco, you sure are beautiful, honey. Position of the sensor chips. So the sensors are all in the center of the joint. What we're looking for is something that would be relevant as as a reference angle. So, you know, like, of course, there's a bunch of stuff that's arbitrary about the angle sensors, sure, but what is this referencing? So it was obvious that the forward position would be one reference, but like, what other reference could it need? The PCB orientation? The PCB, so that's arbitrary. Like, assume that there's just a single arbitrary offset that deals with the PCB orientation, the orientation of the die in the package, the orientation of the magnet on the other end of the sensor. Like, all of that is just arbitrary at manufacturing, but that defines the coordinate system that the rest of this is measuring relative to. So like, what is the other reference point? Com aligned, says Alistair. I'm not sure what that means. Lavach says that's fixed and specified by the datasheet. Within a tolerance, though, like, it's, if you look at the datasheet, it says that the placement of the magnetic sensor in the package has some uncertainty to it. You know, I wonder if this has to do with the way that so if you open each joint, there's an orientation in there where you can see the connector for the motor. I kind of wonder if this is related to that motor connector, which is always in the same place on a joint. You know, maybe I should just get this back into the reference 1 position again and maybe mark it or something. Can the motors be inserted in 3 orientations, 120 degrees apart? The motor orientation relative to the circuit board is fixed because of the way the connectors are mounted. Could it be some quaternion silliness? I have no idea what you're talking about. Like, this, everything here is Euler angles because that's how the hardware is designed. So if there's any quaternion stuff happening, it's going to be on the 3rd microcontroller, and it's not going to show up as a vector like this. It's going to show up as a bunch of separate, you know, 3rd component values. So I would expect, like, if this uses quaternions, I wouldn't expect them to show up here. I think we wanted this one. Yeah, I wonder if this is just the same angle on each joint. Like, if this is pointing toward where the motor wires come out. It's a little hard to see on the monitor, but I think maybe the angle on this joint matches the angle on this joint when I have both of them zeroed. And can I make this one match too? I've got it pretty much zeroed right there. Yeah, I mean, it's a little hard to tell because the mechanical mounts are slightly different on the last axis, but the first 2 axes seem to be at the same angle. And the last axis, it might just be different because of how that mount is attached. This is going to be difficult to replicate, though. Let me see if I have something that will leave a temporary mark on this, so I can mark the locations. just going to use thin strips of masking tape. So the motors are three-phase brushless. They're not steppers. They're basically like the outrunner motors that you'd find in a model helicopter, but they're built into each joint. I'm just frustrated because I think the next step here is going to be taking this gimbal apart and looking for alignment markers. I mean, at least I know how to take these apart without doing damage, so this should be pretty easy now that I mean, this gimbal doesn't have like a bunch of extra stuff in it, so it should be a little easier. And now I'm just trying to imagine what is the relevant reference point. I'm just going to try to stick like a vertical line that lines up on roughly the bottom of each motor, and then we can use that when we're looking closer. All right. So first I'm just going to put down 3 reference marks, which are just at arbitrary locations. I'm just putting these somewhere that's easy for me to access when I'm moving this around. And then for each axis, I'm going to put the corresponding mark right where it lines up to calibration point 1. I'm just adjusting this until it hits 0, and then placing the marker. I'm also thinking about like how would they do this at the factory. I wonder if this is done at an earlier stage of assembly with just raw boards, or if they have a jig that they put the entire thing into that just lines it up just right. I'm expecting that if we partially disassemble at least a couple of these axes, that we're going to start to see this lining up to something, to some important internal structure. My first hunch is that it's going to be related to the connector that the motors mount on. One more. It's at least nice that all of these are independent. And I mean, it's also possible that the axes are all calibrated separately. They wouldn't all have to be calibrated at the same time. That command that copies the calibration, you could just send it to one of the microcontrollers. Okay, I think that's the last marker. So maybe it's time to take this apart and get a closer look at what we've just done. Oh, interesting. Robert's working ahead in the code and saying that one calibration is used in the systic IRQ and the other is used in the time4 IRQ, and they're both used as a simple offset. Yeah. I mean, my guess is that one of these is an offset based on the center position, which is probably a higher level control loop doing heading following, and the other one is an offset related to something motor related, so that might be the actual motor control loop you're seeing. So that doesn't sound surprising, but it's a good data point. Okay, I think there's nothing doing except taking this apart. Power off. Yay, an annotated gimbal. So I'm trying to interpret what Hlavat's just saying, and so there isn't a separate like motor and magnet zero. Everything is relative to the magnet. I was watching a video about the kilogram today, and they were like, but everything is just relative to the other kilogram. And this is kind of the same issue. It's like everything is measured relative to the magnetic coordinate system. So there isn't going to be something that represents the magnetic coordinate system directly. That's just the underlying thing that the rest of this is in. I think I need to move this marking back a little bit so it doesn't overlap the ring that I have to pull this apart via. I'm just going for this joint first because it's the easiest, being in the middle. My little flag is still going to be longer than the section of this that stays in one piece. So taking these 3 screws out should separate the motor on this section. This feels less solidly attached than I was expecting. I'm just wiggling it to try to free this connector. I think maybe the connector is pretty grippy on this one, and the circuit board doesn't have a screw right under this. Yeah, so there's the mechanism. You can see, so this is the motor. The wires are feeding through the center, and that thing the wires are actually feeding through the center of is a magnet. The magnet's just glued in a kind of arbitrary orientation as far as I can tell. And then right under it, that 8-pin chip on the circuit board is the encoder. Robert says the time 4 IRQ handler will in some cases send a command 1 packet back. I think you are finding the pulse width modulation timer. Command 1 is I've seen that sent from the first MCU to the other MCUs when the first MCU is decoding RC servo pulse width modulation style inputs. So are you sure it's sending that back to the host, or you think maybe that might be the command 1 being sent to the other microcontrollers, which I think is I think the port that goes to the other MCUs would be serial port 3. So anyway, just to see all these pieces lined up, so you can see the middle motor, so this is the stator and the motor, and it's free to spin, but this will only assemble when that's lined up to the bottom circuit board, which is the magnetic encoder board, basically. So the magnetic zeroing happens when you rotate this section over to that reference point. And so the question is, when it's rotated this way, is there something going on in here that's kind of a relevant location? Oh. Yeah, I think this is it. Focus. So I think, it's a little hard to see, but I think the intention here was to line it up so that this arm is pointing directly at the motor connector. Because if I line up those two marks, then, and remember this is spinning freely, but if I align this to the right place, then it seems to be lined up with that arm. So that's a good sign. Let's maybe try to verify that on a different joint and put this joint back together, because it's a lot easier to deal with this thing without multiple joints disassembled. Hello, hammer drill. So this is still a bit annoying to deal with on a fully assembled gimbal, but I mean, I could just copy the angles from this one, basically. I might not get it quite as accurate as the factory calibration, but I bet I could get it close enough. So let's take apart the first joint, maybe? Because I would expect the first and second joints to be pretty much the same, and then maybe the third joint is different. Sodium masks, aren't the angles already copied over? No, I haven't calibrated this on the other gimbal yet. So I think what I'm going to have to do is basically just by eye or by machine, like copy these same marks onto the other gimbal and then hold it at that position and run the calibration. But let's see if we can verify this theory first. I think I just need to take these 3 screws out and peek inside here. Yeah, physically copy the parameters and then generate the right corresponding calibration values, I think. So I think the actual calibration tool I make, I do actually want it to start with the calibration from Flash, so I think I'll do a quick extractor tool for that first. But then I want to do the per device calibration using this command that we found. Okay, so then the screws are out. Line this up so the marks match. And then, if my theory is correct, we'll see the connector for the motor lining up with this bar right here. Oh. Kind of, but not quite, actually. That's weird. That's close to lined up, but actually is not that close. You can see the motor connector is right there, and the bar is right there. I wonder how much of this is arbitrary. I wonder how much of this is just they built a test harness at the factory that happened to line things up a particular way, and then they copied it. Don't know what else to do other than manually copy these angles over to the other device. I mean, if I were going to spend a bunch of time on this and make a tool that's like really properly easy for other people to use, it'd be tempting to make a little 3D printed alignment jig that you slip over each of the joints to calibrate that joint. Which might be how they do it at the factory. They might just do it per joint. It might even be an interactive calibration. Like, they might do it with the motors on, and they might have it like homing to a particular place and then taking a snapshot of that. That seems less likely, but anything is possible when you're writing your own factory calibration routines. I guess I might as well take apart the third joint to look at its alignment for completeness, but I'm not really expecting to see a pattern at this point. This is also near the motor. Well, what are we even looking at? What corresponds here? The way the arm comes out from the motor housing is also different for each of the joints. Yeah, this seems very arbitrary. So like there's the motor connector, there's the screw pattern on that side of the motor. Depending, like in the other two joints, see in the first joint the arm comes off one of the long sides of the triangle. And then in the next joint it actually comes off of one of the points of the triangle. And then the long side again. And then that just doesn't seem to line up really. So I'm just going to do this by rote copying, I think, without really understanding what these angles are for yet. Okay. So we're just going to go joint by joint and try to copy these angles. would be really great if I had a way of mounting these things such that they're same axis or something. Yeah, I wonder if I can see any of the relevant parts of the motor through these cracks here. Oh, can I see the backside of the motor connector? I think if you look through the crack in the motor housing, you can just barely see the solder on the back side of the connector. Which for the yaw axis seems to be lining up pretty well with this bar. Looks like Robert found some floating point math. And Paul is asking, do the top and bottom motor screw positions line up? You mean on the two sides of the motor housing? They're the same triangle, but it's smaller on one side than on the other. And I mean, they're free to rotate relative to each other. Oh, you mean in the default? Yeah, so do they line up when I've got this lined up? I don't think so. That looks still arbitrary. Let's check this joint. Yeah. I mean, if they were lining up the screw patterns, the angles would all be like straight down or like a 30 degree or like 60 degrees off from that. Hey, Tuka, what are you opening? Oh, that's fine. He's got a box. I wonder if I can get both of these gimbals on the vise. Tiny coax. Yay, I can do this without dropping both gimbals. Oh, and then Robert says the USART3 IRQ handler has some floating point math. That's interesting. I've been working under the assumption that USART3 is probably the communication to whatever's downstream of this. So if you're looking at MCU 0 or 1, that would be the next joint. And I'd be a little surprised to see floating point, but not that surprised. I saw some stuff in the data segment, or like, you know, in the firmware image plain text that seemed like it might have been floating point, but I didn't look too closely at it yet. Okay, let's cut some more of these. Not all of these are as good as my previous ones, but I wanted them to be shorter. And some of them are still too long. So what I'm trying to do here is just by eye set these so the joints are parallel. There's probably a better way to do this, like maybe using a protractor. And that's not going to stay in place on its own, so I just need to have that ready. Okay, that's our yaw location. I need some sort of linkage. Yeah, maybe. I don't know how accurate this needs to be. I don't imagine that they had an amazingly accurate way to do this in the factory, but I'm still kind of confused about how they're actually doing this, initially. So that's yaw joints. Oh, I think it's more like that. That was just a couple millimeters off. Could this be the DJI CAN protocol? I'm not familiar with that. I'll have to take a look at that. I mean, this isn't using CAN. We saw a little bit of perhaps CAN support in the firmware. I'd be surprised if they were using anyone else's protocol, because it seems like a lot more work to emulate someone else's protocol than just to make one for this. But we can take a look. Okay, next joint. This one was, this one's a little bit back from straight up and down. Oh no, I don't know if I can do this part of the calibration with the camera attached. That might be a problem. I mean, I can take the camera off. It's annoying. And it's least annoying to do it in a way that leaves wires dangling. That might be what we have to do. I think the main way in is through these screws. I mean, I'm debating whether or not I actually want to do this or to try to fake it. Because I could try to calculate what angles these would be, but I wanted to try to just use their calibration procedure. Let's see how annoying it is to take off the camera. I think that's easier to do with this off the thing. This is the link between the original bracket and the 3D printed one that I added, which should be relatively easy to take apart. But it's going to leave some delicate wires exposed, so I shouldn't do this for super long. Lavach is describing an iterative calibration procedure, which is possible, but that doesn't seem like what it... Like, the way the command is set up, I would assume that they're just putting it at a known position and then, like, saving that. It doesn't seem like they're tweaking the calibration bit by bit. It seems like that the existence of that command would make me assume that those are just captured angles from some physical scenario they're putting it in. Oh man, that is not a good fit. But I think it's working out. It's like I need to decide which side of this joint the lens is going to hang out on. I think it's this side. Modern art. This is going to be really imprecise. If I had a protractor handy, maybe I should just print one out. But I think it's pretty much there. I'm just going to put some marks on. That's a bit of a guess, but that's about the right position. And just barely tenable with this set of screws unhinged and the camera kind of hanging by wires. Oh, and I need to get the camera back on the other side of this. Okay. And then this joint. That's almost lined up. Oh, sorry, let me get that on the camera. Just looking at this last joint here. So if I line up the blue tape on here, oh, that is so too dark to see, and Tuco is still yelping. All right, it's still pretty dim, but if I line that up, It looks a lot like these two screws are parallel to this edge, maybe? Which I didn't see a relationship like that with any of the other joints. Well, except for the first one where it seemed like it was the opposite, like perpendicular. Like the neck, on the first one it seemed like the next joint was perpendicular to that edge. Here it seems like the current joint. Oh, but I'm not quite looking at the same thing. Let's try looking at that whole pattern. I don't think it lines up still. I thought I found a pattern that might apply to the others, but... Oh, I don't know. It looks like that it might be... Let me try to get this on the camera better. Maybe we're finding something useful. Oh, Took. Robert is saying a whole bunch of math happens based on some ADC values. I assume the ADC is motor feedback. There's an op-amp for that, but I haven't really looked at how that's connected. Lawatch is asking, how do you know the rotation of the motors? Position is easy. I'm not quite sure what you're asking. Rotation versus position. Yeah, I feel like we're not quite using compatible terminology right now. And then Mike is asking if something looks right. Yeah, that looks right. This is the beginning of the firmware image and the correct load address. Lavach is trying to explain how motor drive works. I get that you have to drive the phases of the motor. I just don't understand what you're trying to say. Like, you need to back up a little bit. I'm trying to reset the chat because I know it's a little broken right now. If the motor can be rotated, you need to drive different phase offset to get the same position. The motor is always in the same position relative to the circuit board, because that's how it's built. And second calibratable parameter. Yeah, I mean, this is like vaguely related to what I've been speculating, but I don't really understand specifically what you're trying to tell me here. Because, like, yes, I know it's a three-phase motor, but we need to get more specific if we're going to have new information about this. And yes, I think it is related to the motor, because when I was changing it earlier, we were seeing the motor basically drive in a weaker fashion while drawing more current, so it was like the phases were not lined up with what I was expecting. So, I mean, all that is there, we just need like specifics about how it's lined up right now. And so I was in the middle of checking a theory. So the theory is that the mounting holes on the kind of secondary side of the motor will have an edge that lines up with the edge of the circuit board. Which, I don't know if that's true. Doesn't really look true for the first joint. Might be true for the second joint, but it's not perfect. I think the only place this really works is the third joint. Oh well. Let's just go back to plan 8.5. What do you want, Tuco? Oh, how about just saying to move the parameter to whichever side makes it stronger to calibrate the motor position? I mean, I get that that's a thing we could do. I just don't think that's how it was done in the factory, which is what I'm trying to replicate right now. Like, this is the way that the command is designed. It looks very much like they have a jig that holds it in a particular position, and then they hit the calibrate button. So, yeah, maybe that's a different way we could do it. That's not what I prefer to do right now. Anyway, I think for this joint, maybe there is an alignment trick. It looks like I can take those two holes and line them up to this flat. I mean, it's possible that they don't actually use this variant of Command-C and they have some different calibration mechanism that they just calculate the parameters with. But the existence of this command tells me that at least at one point they thought this might have been a reasonable way of calibrating their gimbal, which indicates to me that these parameters have some kind of like absolute angular significance to them at least. And that there's probably some jig they have that puts it in a reference position. Okay, that's close to the reference, I think. Lavat says, don't know what might be faster considering the goals of working gimbal. Well, I don't mind tweaking the parameters, but I just want to start with this. I don't want to have to keep changing tactics over and over and over again, you know, and this is close to working, I think. I just don't understand what you're saying. Like, I don't need more distractions. Tuco. Oh, right. So I wanted to start with the parameters from the firmware, so I want to write a little decoder for that first. Let's do this on this computer. So I've got the unpacked firmware here. And near the end, we're going to see the parameter block at a well-known location. Yeah, 18,000 hex. This is where it ends up writing the parameters when they're changed. This is also where the defaults come from. Tuco, give it a rest. Alright, so start, just make sure it can open the firmwares. Cool. So 18,000 hex, and then we're just looking for a bunch of signed integers. Oh, is this using tabs? I can't have that. That's better. I think we just want something like that. That looks right. These are the firmware versions. These are all -1. Are any of these different per gimbal? Or, you know, per MCU? Maybe they all start out the same. Or maybe I made a mistake. I mean, these are not identical binaries. I'm going to make a test change just to make sure that this worked. I think that's it, but let's actually have a real hex editor. Do I have a real hex editor on here? Do I not have a real hex editor on here? Fine, I guess I'll install a hex editor of some sort. This is the one I'm used to using. Oh, I guess MakeOMK spotted a difference. There's an 012. Oh yeah, you're right. Great. Cool. I guess that checks that the extractor is working right. Okay, cool. Well, I don't need to run that experiment then. Let's still install this because I want a hex editor handy. Great. So let's hold on to these. That's right. I had been using this for documentation purposes. Let's repurpose this. Let's also make sure we're working on the right copy of this instead of the one on the Raspberry Pi. Well, actually, I think I want to go back to the Raspberry Pi since I'll want the stuff on that repo, but let me go ahead and check this in. And I'm just going to go ahead and add the sample output here. That could use some cleanup, but this will be fine for now. Okay, let's go back to the Raspberry, just to avoid having to deal with multiple computers right now. I just wanted to do that part on the local machine because I didn't have the firmware images on the Raspberry. Hey, boy. Okay. So I want to change, let's fork this set param defaults and make it two different things. So let's set that, let's make a calibrator. And this will just have a couple of different command line options for doing the different phases of the calibration. And then let's turn the rest of this into just some documentation. So these are mostly working parameters. And I don't necessarily want to use these as defaults anymore, but I want this list to hang out. Then the calibrator. All right, let's keep the warning. And I think I want this to have some command line options. Hey boy, you really want to play, don't you? Where's your bolt? Oh, Tuco. Oh, there's your bolt, honey. Where did that one go? Robert is saying the ADC is probably motor feedback. That would be what I would expect it to be. I don't know why else it would need an ADC. It's, of course, nice to have confirmation. So we want argparse. I hear you, Tuco. cat knows how to push my buttons. So we'll save the default parameters there. So let's just have a couple of different actions this can perform. So we can have set defaults. That's gotta not be how that works. I would assume it to map it like that. To go. So for this, we could just construct the packet, but I think I'll go ahead and add it to this function, or to this. And we saw from the code that we should get a response. So instead of just a send, I'm going to make this a transaction, which includes waiting for a response. To go. I don't think the response is relevant other than the fact that it happens. The code just had some hard-coded values it put in this packet. Oh yeah, this should take a list of targets. So by default, it'll work on all the micros, but you can tell it to work on just one in case we want to calibrate the angle separately. Let's split this up a little bit. Not very much, but sure. Let's just keep that easy to find, that little warning. Dangerous. Calibrator. Great. So we ran something like this. It's not going to do anything because the gimbal's not plugged in, but let's hook this gimbal back up and actually see if we can make this thing work. And it's certainly possible we might end up tweaking the motor-related parameters like Hlavach keeps suggesting, but I think this is going to be a decent way to get started. Doing this with the camera dangling like this is really annoying. I can hold all the joints into the right position. Let's see if I can also get this plugged in. Oh man, why all the noises? Robert is asking if the RAM dump is from before or after the gimbal got sad. After. All of this is from after the gimbal got sad. The RAM dump was probably also while it was not running, so a lot of stuff might have been turned off. Okay, I can hold it into the right position. I'm just a little worried about this falling now, because there's not much actually holding the camera. Let's prop that up. Okay. Alright. We need to power on the gimbal without it actually running, so we need some program responding. So it doesn't really matter what we'll do. We can just use param diff or something. And so wait for the gimbal to connect. So gimbal power. Okay, that's fine. So we have calibrator. Who's calling set motors? Is that something left over? Oh, geez, I forgot to kill this. Okay, that's a little safer. Great, connected. Cool. So let's just give this the actual defaults now. Set defaults. Seems good. Then I have it close to the position 1 already, so let's do this next. Cool, we got a response. And let's try the other position now. This one should just be the center. And this one will be easy to tweak later because I don't have to have the gimbal or the camera partially removed. Okay, another confirmation. And let's just save this now for good measure. And then let's try the calibration tester that we wrote earlier on the stream. Calibration checker. So we should see this pretty close to the cal point 0. So that looks pretty much right. And then if I home in on the previous point, I'm not going to necessarily do this in all the axes, but like now you can see, at least for the yaw axis, that matches our stored point 1. So I'm going to tighten the screws on this camera and then turn on the motors. These brackets are all 3D printed in Tallman tea glass, which is a type of PET plastic. So it's pretty strong. It also makes a weird kind of squeaking noise as the screw gets snug. Oh, this bottom screw still has a little ways to go. There we go. Bottom screws, tightish. That's better. All right. Well, I think we should just turn on the power. Whereby just turn on the power, I mean turn on the power very carefully with the UI up monitoring everything. So let's run this param server. This is the thing that well, I wrote this between streams, but we used it a bunch on the last stream for the first time. This gives you a WebSocket-based server that you can connect a little HTML UI to. So we've got a little gimbal dashboard. All right, it's pretty small now, but so these two I think are related to motor power. These are the two things that we just calibrated, 4D and 6.4. And there's a bunch of other dynamic stuff, some of which I've annotated. But let's try hitting the motors. That seems pretty settled, doesn't it? I mean, the center's a little off, but power consumption is really low. Like 120 milliamps or so for the whole thing. Or not the whole thing, but the gimbal. I'm reading a total of 460 milliamps at 12 volts, and the camera plus LiDAR takes like 330 of that. The center is obviously off a little bit, but that could be coming from some... Oh, I didn't reset the heading, so that could be coming from this, maybe. Yeah, I think I still don't fully understand how to reset the heading, because this is supposed to be a heading of 0. But one thing I could try, now that the gimbal seems to be relatively unsad, is just to power it up without the software attached and let it go into its normal like RC servo controlled mode. Because then at least it should have pretty well-defined behavior, like it should point forward and track slowly, so we can at least see if that works. This is looking really good so far. I agree with the GIF. This is definitely a yay moment. So yeah, let's reset this. So I'm terminating this, so nobody's listening to the serial port. And now let's just use good old-fashioned power cycling to bring this thing back into its default mode. So off and then on. It's centered. It's like actually centered. I mean, it's probably as centered as my calibration was, which is good. So whatever other thing has been drifting that we're not resetting over the serial protocol, it's working now. I think we unsaddened our gimbal. Ooh, look at it follow. I think we should try out the video output from this. Let's get an SDI input. This tiny coax. Crotch cam. That's gonna get me banned from Twitch when this thing goes crotch cam. It's looking pretty stable. There we go, boob cam. Hello. Oh, that's beautiful. I think we unsatted the gimbal. So there's still some question marks as far as controlling it properly over the serial protocol, since it looks like there's some stuff related to the general like heading follow mode that we still don't really understand how to control, and I think it probably starts up in kind of a weird mode when I'm using it the way I have been programmatically. So that's still maybe that's another thing to do via reverse engineering. So we already know there's a command that we send during startup that takes it out of kind of its normal PWM controlled mode. If we look at that in the firmware and see exactly what that disables and kind of how we could recreate that stuff by hand, then maybe that would be another way to proceed. Robert says at this point I would just patch the firmware. Patch it for what? So yeah, so right now I should be able to command it with like RC servo commands. I would have to change my setup again to send it that, and I don't feel like doing that. I'd rather continue with the serial port. But can we see that side by side with the camera? Actually, I should have a little pop-up overlay for the DSLR I can put up on here. That's not a good place for it. Hey Tuco, I know I took your camera. It's looking pretty good. I hear you, Tuco. You want to play? Maybe it's time to check this into GitHub. Yeah, this is looking good. I mean, maybe my calibration could use some tweaking, but I think it's definitely close enough. Hey, little guy, what do you think about CapCam? Whoa, sorry about the angle. You just went out, that's fine. All right. So, I think this is going well. I think this could be a point to wrap up the stream, but I think I've still got some energy in me for streaming, so maybe some more reversing. We can take a look at how the controller part of the firmware works. Oh yeah, and so we're also not seeing drifting right now. I haven't gotten to the bottom of what the drifting is, but I think that's related to something in the part of this that is normally disabled. Well, the firmware that's responsible for the PWM inputs that's normally disabled when I have that in serial mode, I think that is calculating like basically a velocity at some point that the loop integrates. And so I think I probably just need to figure out where that is and like set it to 0 or set it to the value that I want, because right now it's probably just lingering at something non-zero sometimes, causing the drifting. Oh, Lavach says after it moves in X, it drifts for a few seconds. That's just the regular follow mode, unless I'm misunderstanding what you're saying. So I move, and then it just catches up with the new location. But that's not the drifting we were talking about. The drifting we were seeing earlier was just continuously moving in one direction. You see it moves, and then it should come to a stop right there. That's looking nice. But the drifting we were seeing before would have just been it continuing to move very slowly. And it was hard to see in real time. If you look at the time lapse from one of the previous streams, it's really obvious. But yeah, right now, as far as I can tell, it's working perfectly. Like, this is exactly what we expect the gimbal to do. So I think I've just gotten this back to the point before it got sad. So now I'm armed with much more knowledge about how these things work. Now the task is back to how do we control it over the serial port. So I think that's pretty close. And MM1 is asking, could it be rate versus absolute position control, like in the GTI protocol? Yeah, probably. I mean, I haven't looked at, like all these gimbals probably do very similar things. Like, I've looked in a really cursory way at the, what was the name of the Alexmos gimbal, and I think I might have seen some details about DJI, but I didn't really go deep in that. But yeah, I suspect that this has multiple ways of controlling it, and there are probably flags that turn on and off, like a follow control loop per axis. And I suspect that what we're seeing is the result of having different control loop flags set on the different axes, causing them to act a little differently. But at this point, we're going up to a higher level. So before, we were having trouble with just the basic, like, controlling the motors and keeping them stable. And so I think those two angles, or especially that 6-4 angle related to the motors, that was just necessary for giving the motors the amount of power the control loop was expecting and keeping it stable, and keeping it from differing in power depending on what the angle was. So now that all of that is settled, I think we're back up to the higher level control loop, dealing with things like the follow mode and everything else. Apparently, by this point, Robert would have written their own firmware. Well, would you like to contribute firmware? Not really sure what to do with that comment. Lava just saying it might be trying to compensate for quadcopter rotation. Yeah, I mean, obviously it's following at a particular rate. You can change that rate. And I mean, these gimbals are used not just for quadcopters, but also for handheld stuff. And I'm sure you can set the parameters a little differently for those. Yeah, power and direction. Like a lot of the motor control ends up working incorrectly when this calibration isn't correct. Anyway, I think we're mostly on the same page there. We gotta pull. I don't know that this passphrase is helping even in the slightest. Anybody who cares enough to look really closely at the video has it, so I'm not relying on it for security. I think it's mostly just an annoyance. Anyway, so that's all on GitHub. I think that settles the calibration. I think now I am mostly concerned with, where was it? Command B. Yeah, this one that I've been calling PC init. So when this command goes out early on in initialization, it prevents the gimbal from starting up in its kind of RC servo style control mode. So what I would expect to see is, so this is looking at the parameter. The parameter has to be 1 if it's not 1. And then here, yeah, it's just writing 1 byte to this flag here. So what I would expect is that maybe there's like a timeout, and then after the timeout expires, it checks this flag and then uses that to initialize one thing or the other thing. Robert says, my guess right now is the unknown calibration is for motor field-oriented control. I mean, it's almost certainly something that's related to the motor positioning. It's just really unintuitive when you look at it from the outside, and it doesn't seem to match the connector on the motor or anything like that. So yeah, I mean, it's probably lined up to something internally in the motor, but I guess my question is, like how do they actually calibrate it? And I think they just have a jig that holds it in a particular angle. Like I think it's basically just a more automated version of what I just did, but it could be something else. So let's see where else this flag is used. Maybe we can switch back to the cat cam since we've got that. We don't need the gimbal on right now. Oh. Fine. Fine. Well, I guess you have your own plans. That's cool. Okay, main. So also I think this is not only a flag, but the base address for an array of flags, so we might have some false positives here. This seems to be potentially what we're looking for. This is reading that exact byte, unless there's something in between there, but probably not. That's interesting. This has some stuff we've seen before. Oh, this is from the Systic ISR. Okay, where else? So that's something from Systic. Oh. I wonder if this is the timer they're measuring incoming pulses with. Tuco, jeez. Tuco, what do you want, buddy? Ow. Some sort of wiggling around the center position. I feel like Klavach and I have been completely misconnecting on this stream. That's interesting. I wonder if this is... if this like port that it's using can have multiple uses, and... Let's save this for later. Let's look at other cross-references. This one... Ooh, this one's huge. Let's get some more screen space. So here's where it's checking the PC flag. So I think all of this stuff ends up getting skipped if the PC is attached. Is this where we're actually sending packets to the other? So I think this is related to sending packets to the other microcontrollers. And I think this might be so command 1. So I think this is microcontroller 1, so the next microcontroller after this one, and then command 1, as in the data from the joystick inputs. And then would this be the actual packet? Yeah, I think this is, I called this packet in, but I think this is actually an outgoing buffer for packets going to the next micro. Oh, I'm doing some math here, multiplication and division. What would be really nice to know is how the current microcontroller handles this same data. So I'm expecting this as part of some control loop, but I don't know the context for this yet. That's one of the next stops, but I just wanted to spend a little more time with that piece. This might be the follow loop. This is looking at the distance from the center position. What's the scale factor? Multiply by 36,000. So doing more fixed point math on this. 20-bit fixed point maybe? Oh, and this is checking the motor on-off flag. This has got to be some kind of control loop thing. Timer 4 ISR. Cool. So let's rename this time 4 sub 1 and time 4 sub 2. Probably just acknowledging time for ACK and time for body, maybe. So this is the section related to the PC being attached. feel like this would be easier if I had more landmarks in this firmware. Like knowing about, like having more of the parameters and hardware functions notated in here would help. I wonder if this is checking whether the input is in a particular range. I would also expect to see, like on whatever's happening for joystick input, I would expect to see it happening twice for pitch and yaw, because this microcontroller is responsible for reading pitch and yaw for the entire gimbal. That command 1 might be the best starting point we have. I don't know the structure of command 1, but we saw it being sent from the first micro to the subsequent micros. It seems to correspond to joystick input in some way. I think it's 3 signed integers and a 1-byte mode. So this would be the length. And this would be a pointer to the command buffer. Yeah, so I think this is padding or something unrelated, and this is the beginning of the command 3 half words. And right after that, we should see like a mode byte. Is that this one? No, that's... yeah. I don't actually know that's mode, but I'm going to call that mode-like byte. So I'm looking for R1 right now, which is the first word from the command. Interesting. Is this a center position? 15, 20? That's kind of arbitrary. No subroutines that might be returning that? I don't think so. What about the next word? R5. Sign extend, negate. Clamping something to a minimum of 1,000. I wonder if this is milliseconds, or microseconds rather. Yeah, we're clamping something between 1 and 2,000. We're loading it from here. And related second. Oh, that's the only place that's used. So maybe this is a temporary value. See, that's definitely an offset relative to this, that data structure. But maybe we only refer to it by this address. Commando 1 related. We have an XDI ISR, which might also be related to the internal, or to like joystick stuff coming in. It's just these two places. That's sent over here. Yeah, this is pretty straightforward looking. This is just checking different external inputs. So we have two of these blocks. I think this might be the two inputs, like pitch and yaw. Different. What is this? This is probably some hardware that's attached to the pitch and yaw inputs. Let's see if we can find it in the datasheet. Oh geez, did I lose my video input? It just froze. Hello, video. There we go. We have detected you're about to open a datasheet on YouTube, and we have taken precautionary measure of halting your video capture. Okay, so this is like the brief. This is the manual. This is the programming manual. So this is what we need. The programming manual was just for writing to Flash. And the memory map. Four 4001-0414. That is the external interrupt registers, no surprise there. So we're storing something, presumably to acknowledge an interrupt. This is probably just going to be resetting and storing the value for like one of the pitch and the yaw. I'm going to call this PWMN and just name these PWMN1 and PWMN0. And then PWMN XI handler. And so R0 is this data structure that I assume it's going to be writing timing into. Yeah, I'm not going to go super deep into this, but this is probably calculating microseconds. And so one of these is going to be pitch and one of them is going to be yaw. So XDI is for capturing that, and then here's us using it, and that seems to be the only two places. So we should see one of these, and then PWMN1, the other one close by. Oh yeah, there it is, PWMN1. I wonder why it always reads 0 and conditionally reads 1. Maybe this is pitch and this is yaw, because it has modes where we don't read yaw at all. I'm going to call that pitch maybe, and this one yaw maybe. And that might make this test kind of mode related, although I don't know why we'd be comparing that there. This is related to R0. Oh yeah, this is probably a mode. Where does R4 come from? Like way up here, maybe? Huh. So R4 up here is motor on-off state. And so IDA's just propagated that through, and now we just have all these other flags that are nearby to R, or to that same motor on-off state. Can we get it to expand that then? I guess it hasn't tracked that all the way down here. I don't know how to tell IDA, like, I know the value of R4 right here. But, I mean, we can figure out where that goes. It would just be nice to have that linked in IDA. So that should be 4 past this. I'm going to call that PWM in mode state since maybe there's a better name for it. User control mode. I think this is going to be the thing that you set by kind of holding down the button on your transmitter that's connected to the third input. Oh, Robert says 1520 might be like a midpoint on the PWM signal, like a default. Yeah, maybe. It might also be like a dead zone or something along those lines. Like maybe they say, like, if it's not more than 1520, then like set it to 1500 or something. Let's see if anybody else is using this variable. Lots of people loading it. For storing to it, ooh, is this going to be setting a default control mode maybe? This is setting the control mode to 1. I think that's checking whether the PC is attached. So R4 is a base address for a bunch of things, but it points directly to that main flag PC attached. If I'm following this right. So like this, for example, is testing whether the PC is there. Oh, this is sending the response to the PC. Hello, computer. This is the target. This is the command saying hello back. And I think this is the length. Cool. So, branch if not 0. So I think this is actually not like computer attached. I think it's like a standalone mode. So if it's 0, we're saying hello to the computer. If it's not 0, we're going over here. Does that jive with what I saw earlier? Jumping if the main flag is not equal to 0. That's more like PC attached, because we would want all of this. Presumably we want all this only when the PC is not attached. Oh yeah, branch if not equal to 0. So if the PC is attached, we skip this. Yeah. So how does that explain the thing that we just found in main? Compare and branch if not 0. This looks like the command where we're saying hi to the computer, but this logic seems backwards. Maybe this is not responding, but maybe this is asking. And we're just avoiding sending it unless, like, if we've already sent it. This is in a loop. Oh, right, because we send this multiple times. Okay. I think that's what's going on. So we send this if we haven't yet attached. If we have attached, are we passing this on to the next micro? Is that what's going on here? Yes. So I think this is related to having that computer connection passed on from the first micro to the next and the next and the next. So if we are already connected, then we're passing this message on to the next MCU. If we're not connected yet, then we spam this out to the host and give it an opportunity. And then we're polling for serial in this loop. This one is probably going to be something related to getting a command. Okay, I don't really care what this is, but this is definitely the part where we connect to the computer. So that's neat. Well, let's see where else this takes us. So systic, timer 2, serial read. What's using this in serial read? Where was that? Oh, it's way down here. Ah, that is where we write that flag. And we're always writing 1 to it, regardless of what came in. So in main, this is for connecting. In serial 1, that's for connecting. So then time 4, time 2, and systic seem like our 3 control loop locations. Oh. Do we jump over all the systic when there's no... How does this work? PC attached. So if this is not equal to 0, so if there is a PC attached, we run these 2 instructions. if there's no PC attached, then this will be 0. And let me jump over this. And what are we checking from R1? Oh, maybe there are different values this can take on besides 1. Seems like 5 and 3 might be relevant. This might have something to do with the control style. And then this is something that has a lookup table. This is probably like a logarithm or something. I mean, it seems like they might want to have nonlinear response for the controls, and so maybe this is like a nonlinear mapping for that. This looks like more fixed point math. And so more math, more lookup tables. Yeah, this is probably some kind of fixed point math utility. Or this might be something a little higher level. What does this split into? These just might be quadrants, if this is like a trig function. Well, it has more than 4. Anyway, I'm pretty sure that's just fixed point math. So yeah, some part of that is controlled by the main flag, but that's not quite as interesting. I think I'm going to go back to where it was sending those command 1s, because that was pretty nice. I think that was in time 4, but maybe I'll briefly look at time 2. These are some more params. I should really write a script to just name all these parameters. Oh, that's right. This VM doesn't have IDA-Python working for some reason. I need to fix that. Because normally I would just write a little Python script to name all of these and set them to the right width. But I think that's a yak better shaved off screen, probably. Yeah. This is interesting. I need to actually figure out what these are. So, I really just want IDA-Python right now. I guess I can name a couple of these manually, but ugh. Let's call that param O. Let's just skip down here to these. That was 272. So 272 is param 13. Okay, so param 18 turns into R7, which is what it's checking down here. So is this like an alternate? It's like, it's interesting to me to have a parameter that supersedes is the PC attached or not? Because I'm wondering if this is something that would be useful to set once we are attached. What does that look like in my chart over here? Param 18. That is set to 1. This seems like a useful on-off flag. Like, it might be useful to just try turning this one on and off and see what happens. Okay, so now we're back in, what is this, time 4? Yeah, and this is a really big timer callback, and this is where I think we're actually taking the pitch and yaw from the PWM input and turning it into commands for this and the next micro. And so part of what I'm interested in is, like, I've been able to send just the same command to the other micros, but this micro is not listening for this command on the serial port. So I think I need an alternate way of getting commands in. I don't think actually sending command 1 is going to work, because this micro can't listen to it. And so this is the packet going out to the next micro. So what is it doing with these numbers? This is the one that might be pitch. These are offsets relative to the data structure that the PWM inputs take. So like one of these is probably microseconds. It's like a flag thing. Yeah, so maybe this is like a present or not signal, and this is like the microsecond value. Maybe this is a default. So I'm going to assume this is the pitch control joystick input. That just goes right into there, I think. Of course, maybe this microcontroller doesn't need any of this. Maybe this all goes to the last micro and then it does all the work. This is sending it to the next micro rather than directly to the last one. What about R5? Well, actually, I just want to follow this next. This one that's probably yaw. So, again, 12 seems to be a flag, and 8 seems to be microseconds. So here we're clamping it. So in this firmware, the way it uses pitch is it maps that pretty much directly to angles, and the way it uses yaw is that that turns into a speed. So I would expect them to be used a little differently. Oh, I think Robert's already made some progress plotting the lookup tables too. He found like sine and cosine tables, and another one that looks like a scaled exponential of some sort, like what you would do for fixed point exponential probably. So these are min and max. R2 is probably in microseconds again. Is this a middle position? Yeah. So I guess yaw is in different parameters. Like maybe pitch is in microseconds and yaw is, it looks like scaled by something else. Where's R5 coming from when we don't take this loop? 0. So I think this is the output of the whole scaling contraption for yaw. Interesting. This might be where the yaw drift, like this might be responsible for accumulating yaw, but that's probably also happening elsewhere. Yeah, I think that stays in R5. I think we're using it in a couple of other places, but... So, second word. Scaled yaw input. Now what is the third word? Because we only have 2 inputs other than the mode, and the mode seems like it's done in a different way. Like the mode had an analog circuit that seemed to be doing pulse length detection before it gets to the micro. So R8 for the third word, and then R0 for the mode thing. R8? Can we treat this as a negative number, please? I forget how you do signed numbers in IDA. I guess I can say hex for now. Is that related to the current yaw? I think that's the current, like the yaw command versus the current yaw. I don't know if I need to be super detailed about this just yet. I'm trying not to get really, really deep in areas that I don't need to be in. So this might be a current yaw. And then we're just left with this one byte. Which I would really expect this to be the mode. Here's setting the mode again. So that's all relative to R4. Yep, that's user control mode. Sweet. User control mode. This isn't in the parameter space, is it? No, this is elsewhere. But is there a path from the parameter space to this, like if I wanted to set user control mode? This is going to be a little hard to grep for because we have so many places where the offset ends up getting lost. Here's one where it didn't. This is setting the control mode to 3. Oh, and here's 0. This isn't like a serial accessible thing, is it? So, like, just to bring this back up to a slightly higher level discussion, what I'm trying to do right now is to try to find. So I know how to calibrate the gimbal at this point, roughly. The next step is how do I control it? And so I've seen this command 1, which I can send, and I can get the first micro to reproduce to the next one. But I'm trying to figure out how, like basically how the input path between joystick and internal state works, and which pieces of that I need to provide on my own when I boot the micro up in serial connection mode. So what is this? Oh, this is in time 4. It's based on this parameter, whatever this is. I think these are definitely pitch and yaw. I think we can remove the maybe. Alright, I gotta take another restroom break, but luckily the cat is on the rack, so unless he follows me into the bathroom, we'll get a little bit of cat cam. I need this to be taller. Oh, Chico stayed put. You know, it would be really nice to look for a handler that's receiving this command 1 on the other micros. It'd be nice to know whether the next micro, number 1, even has a handler for command 1, or whether it just passes it on to the next one. And then, if that's the case, I would expect all the actual logic to be on the last MCU. You know, I wonder if we should just try sending command 1 again, because I had a program all ready to go that did that. I just wasn't really getting much in the way of results because it looked like it was in the wrong mode for that to work. I think that's probably still going to be the case. I think if we don't understand this a little better, I'm not going to get useful results out of that. All right, well, you know, I'm finding this environment is bothering me somewhat. I really want my IDA Python back, and I think I just need to get a different IDA VM set up for that. So this might be a good time to wrap up the stream, and I'll do my IDA Python and maybe do a little bit of poking around in here, but we'll see folks on the stream again if I come up with anything good. So I think generally I just want to know how to control the gimbal, and I think some of this is going to boil down to understanding some of these mode flags and being able to know, like, well, how do I turn on and off, like the follow loop, for example? How do I, how do I give it a velocity versus how do I give it a target? And so these are things that I think I just need to spend a little more time with, like IDA on perhaps a larger monitor and with more plugins. So I think that might be about it then. So just to recap, this was a pretty successful stream. We got the gimbal unbroken. We wrote a little calibration tool. The calibration is based on stuff that we found in this disassembly. There's a new command that you can basically just tell it to save angles for later. And there are two of these saved angles. There's one that's the center position, and then there's another one that seems to be pretty arbitrary. My speculation is that it's related to something salient to how the motors are oriented. Like, you know, here's the boundary between like phase 1 and phase 2 or something. But they seem really arbitrary, and I couldn't find anything that consistently lined up with them even when taking apart the gimbal. So I just kind of copied the angles from a working gimbal to physically transferred the angles to a working gimbal and then calibrated it in that position, and that seems to work. So yeah, I think the next step here is, we're back to trying to control the gimbal rather than trying to unbreak it. So just doing a little more digging in the disassembly to figure out how all the different flags work so that we can control that pretty effectively. So more IDA, more Python. That should be nice. This VM is kind of in a bad state, so I think I'm just going to find a fresh VM or install Windows on a fresh VM, and I'll have that ready next time. In case anybody is into playing along at home and you haven't already seen this, I've been keeping all of my work here so far on GitHub. So if you go to GitHub /scanlime /Feiyu Gimbal. Tools for talking to the Feiyu Tech Gimbal via serial. All the stuff we're doing here is right over here, including the brand new calibrator, which I wouldn't advise running unless you have a very sad gimbal, but if you have a sad gimbal, it might help you. And I think that's pretty much it. I've got a little bit of stuff for the firmware. If you download the firmware, you can use this tool to decrypt it. And if you decrypt the firmware, then you can use this new tool to extract default values from it. And here's some sample values that I got from the firmware 1.15, which are very similar to the values we pulled out of a live gimbal, but of course they're missing all the actual live stuff and don't have any of the calibrations stored. Sad gimbals got you down. This tool is for you, says Wesley. I couldn't agree more. So yep, that's pretty much it. I will see you on the other side on the future streams. And here's a moment of Tuco to end the stream with. He's so peaceful. Happy hacking, folks. Keep taking things apart and documenting it. It seems to be working.